When building a data architecture, there is exactly one non-negotiable objective: perfect state preservation. The data you extract at the source must arrive at its destination without losing a single drop of its original semantic meaning. This is the mathematical guarantee of invariant state preservation. The reconciliation error between origination and consumption must be exactly zero. In the datatism framework, achieving that zero error means passing the original truth through 6 transformational operators: time, transformation, traceability, trust, technology, and team. When any of these operators corrupt the state, the pipeline fails. This breakdown is the root cause of systemic architectural misalignment in modern production systems. Preventing that decay requires a unified approach. Data engineering and data science cannot operate as isolated software silos. They must be governed as an integrated system stack under a single taxonomy. While both disciplines live in the exact same data ecosystem, they process that data using diametrically opposed mathematical substrates. Data engineering acts as a structural, deterministic engine. It relies entirely on discrete mathematics and hardware mechanics to guarantee absolute exactness. Data science operates as an inferential engine. It embraces uncertainty, using continuous, probabilistic mathematics to approximate reality and optimize predictive models. These two opposing mathematical domains are forced to interact inside the transformational operators of our pipeline equation. To master system architecture, we have to deconstruct these operators. We need to map exactly how data engineering and data science weaponize different branches of mathematics to achieve their distinct goals. This equation introduces the pipeline tax. Time through team dimensions represent the operational tax required to transport truth. If origination and consumption were identical, pipeline length collapses to 0. Because we transport data, we pay this tax. Let's isolate the technology operator. Data engineering operationalizes technology through bitwise mathematics and hardware memory interleaving. This requires aligning vectorized memory buffers to strict 64-byte boundaries and packing data across 1024-bit SIMD register strides. By exploiting this discrete math at the silicon level, the pipeline reaches maximum physical throughput, decoding hundreds of billions of integers per second. Data science approaches the same technology operator from a completely different angle. Instead of physical silicon execution, it relies on abstract semantic execution. It operationalizes technology through GPU tensor transformations and constructs high-dimensional spatial indexes, like hierarchical navigable small worlds. Both of these domains use the term vectors. But where data engineering uses vectorized registers to maximize cache execution speed, data science uses vector spaces to map contextual spatial logic. Engineering a scalable technology dimension requires simultaneously optimizing the deterministic math of silicon layouts and the continuous mathematics of spatial models. Moving down the pipeline, we encounter traceability and trust. Data engineering guarantees traceability deterministically. To do this, it relies on graph theory. By structuring pipelines as directed acyclic graphs, architects enforce rigid orchestration networks and exact one-way table lineage tracing. For trust, it relies on cryptography. Engineering uses hashing algorithms like SHA-256 to mandate absolute verification of state changes across distributed logs. Data science replaces this strict exactness with probability. Rather than proving a single programmatic path, it traces feature-to-model lineage using explainability models that estimate complex behavior in continuous space. It handles trust using probability and information theory. Data science measures feature shift over time using KL divergence, or injects differential privacy noise to intentionally mask exact states for security. In the engineering layer, traceability and trust demand cryptographic exactness. In the modeling layer, they demand the strategic management of uncertainty. At the computational core of the pipeline is the transformation operator. Data engineering roots its transformation layer entirely in set theory and relational algebra. It manipulates discrete sets to guarantee exact database joins, projections, and ACID-compliant state mutations. Data science abandons discrete set operations entirely in favor of multivariable calculus. It transforms continuous tensor inputs by mapping them against differential loss functions. Models compute vector gradients and use backpropagation to continually adjust parameters and navigate those complex surfaces. The underlying motives are completely different. Engineering transforms to preserve structural integrity. Science transforms to minimize predictive error. Yet these radically different mathematical operations execute inside the exact same data ecosystem. Any scalable architecture must simultaneously support Brediet relational algebra and fluid continuous optimization without corrupting the original truth of the data. Reassembling these mathematical layers reveals how the transformational operators act as the interface between raw math and organizational goals. We have seen how data engineering and data science utilize different mathematical substrates to solve for these same T dimensions. By stacking these operational roles on their mathematical roots under a unified diagnostic roof, a four-tier architecture emerges. Tier 1 provides the governing taxonomy. Tier 2 provides formal logic. Between them, Tiers 3 and 4 act as operational pillars, bridging hardware mechanics and inferential modeling. Achieving the ultimate goal of zero semantic decay requires integrating all four levels into a single operational framework. System architects use these T dimensions to isolate and diagnose specific critical failure points within massive, complex data pipelines operating at scale. When a pipeline fails, the framework allows you to pinpoint the specific mathematical domain where the state was lost. You can determine if the issue is a data engineering state decay, like a broken join or memory layout failure along the discrete axes, or you can identify a data science training serving skew, hidden deep within the probability distributions of a continuous feature space. A data problem without a defined dimension is simply an observation without a diagnosis.